Bit Simply 5. Learn, loop, evolve.
Welcome to Bit Simplify. Today, we're staring into the abyss. Popular culture often portrays a black hole as a two-dimensional drain in space, or a cosmic vacuum cleaner roaming the galaxy to suck up nearby stars. In reality, a black hole is an extreme amount of matter crushed into a tiny point. Imagine taking the entire mass of the Earth and crushing it until it fits into the palm of your hand. Under that weight, the fabric of space and time warps. The density is so high that the surrounding geometry of the universe changes. A black hole is a physical mass so heavy that it forces space to curve in on itself. To understand the behavior of these objects, we have to look at the speed of light, the 300,000 km/s limit that governs the universe. Since light has no mass, gravity cannot grab it like a solid object. This raises a question: how can a black hole trap a beam of light? Albert Einstein solved this by reframing gravity as the physical curving of spacetime. If the path itself is curved, even a massless light beam must follow the bend. Physicists use the river model to visualize this. In this framework, we stop viewing space as a static grid and start seeing it as a moving fluid. To grasp a black hole, imagine a cosmic waterfall where the physical space around you is crashing toward a center point. Let's follow a space probe moving towards this waterfall, starting from a region where space is relatively flat. Out here, the river of spacetime drifts slowly towards the center. The probe has enough engine power to turn around and fly back upstream. As the probe enters the ergosphere, the flow of space speeds up, moving closer to the speed of light. This diagram shows the movement of spacetime around a rotating black hole. Space falls inward while twisting, dragging the probe along a circular path. The probe spends massive energy to resist this, but because velocity arrows point outward, escape remains possible. The approach to a black hole is a physical struggle against an accelerating, rotating tide of space. Eventually, the probe reaches the edge of the waterfall, the event horizon. At this boundary, space is falling inward at exactly the speed of light. This model shows an outward-pointing light beam trying to swim against the inward flow of space. Since the river is moving at the speed of light, the beam makes zero forward progress. It hovers in place. This image from the Event Horizon Telescope captures the shadow of the black hole M87. The dark center is the region where the current of space has officially outpaced the speed of light. The event horizon is a mathematical point of no return, the line where the fastest thing in the universe can no longer move upstream. Once the probe crosses that invisible line, it instantly enters a region where space flows inward far faster than light. The curvature of space is so tight here that every possible direction, left, right, up, or out, folds back towards the center. Every path leads to the singularity. This is the center point where density is infinite and our known laws of physics no longer apply. Inside the horizon, the concept of out no longer exists. The singularity is the inevitable destination for all matter. Now, let's watch the probe's journey from the perspective of an observer staying at a safe distance. In the river model, light signals are like messengers swimming upstream to reach us. As the current speeds up near the edge, it takes longer and longer for each messenger to reach the distant shore. To the outside observer, the probe appears to slow down. Because the signals are arriving at a slower rate, time itself seems to decelerate. This chart tracks the energy loss of those light signals as they struggle against the inward flow. The waves stretch out, becoming dimmer and redder, a process called gravitational redshift. Because of the way light and space interact, an outside observer never sees the probe actually cross the horizon. We only see the image of the probe as it approaches a standstill. From our perspective, the probe freezes at the edge, fading into a red ghost that eventually vanishes from sight. While we see a frozen image, the probe has already experienced its fall down the waterfall and into the singularity. A black hole is a region of the universe where space flows faster than light. See you again tomorrow.